Hi, welcome back. In this lecture, we are going to simulate the backward facing step using the Reynolds Stress Model. In particular, we are going to use Launder-Rees-Rudy model. For this, we'll first copy everything in the k-epsilon model. In this LRR model, we have two variables. One is the Reynolds stress and another is the epsilon. So let's copy this to LRR, a new folder. Here you can see the new folder which is created. We'll go here and remove everything. Let's go to KLRR, and before removing everything, we want to do a little bit of pre-processing which is recommended to initialize the Reynolds stress. In order to do so, type the following: simple form, then we are going to post process for R Reynolds stress, we are going to post process for the latest time. If you now look at the latest time, you'll see that this is created, and we'll copy this to the 0 folder, right, and rename this as R. You can also rename it here. So notice that this Reynolds stress is already at steady state. You may ask that why are we doing this? We are already at the steady state using the k-epsilon model at t equal to 2000. So why we are again using that stress to solve using the LRR model? The idea here is to show you that in the LRR model, even though in k-epsilon model we found that the primary vortex is stable, but in case of the LRR model, you will see the unsteadiness in the flow when we simulate. That unsteadiness is inherent to the flow at this high Reynolds number, which is 36,000 in our case. Now we can change other properties of this model. In the turbulence properties, write LRR here. So go to the system, and in the FE scheme, we have to add two more terms. One is phi R and another is just the divergence of R. For the divergence of R, remember that only this particular discretization works. So you can try other and see whether it works or not. In case of this term, which is the viscous term, the discretization for this is Gauss linear. In case of Reynolds stress, we do not have a new effective. We can remove this. And once this much is done, we also need to add R here in the solver, as well the relaxation factor for R as well as for epsilon. So for both epsilon and R, we need to have a very small relaxation to make sure that it is stable. Even though this will be a transient simulation, we'll show that in the steady state simulation, while solving this using a simple form, we'll find that this simulation will be unsteady and will be unable to converge. And therefore we should not run simulations using the LRR model for steady state because it is harder to achieve. We should always run a transient simulation. Let's run simple form. Let me clean everything. Form list. We removed everything except this, and now run simple form. We also need the wall distance in the scheme. Go here and type wall dist, and the method is we are going to use mesh wave, and then we will run this. Let me also make sure that we are saving all the results. So in the control dict, we'll purge right, make this 0 so that it saves everything. So once this is done, you can view the results. You can already see a lot of vortices here. Let's look at velocity. In velocity, we don't see anything going on here, but as soon as we reach the step, there is a lot which is going on. So we'll look at the LIC plot and see how the vortices are developing and how they are moving in the space. In the initial stage, we find a lot of vortices. These are here because we used Reynolds stress, which was the result of the k-epsilon model. In order to correctly simulate this, we should also initialize velocity and pressure. So we have not done that, even though that Reynolds stress is not entirely correct, but still we'll have this kind of which keeps on generating. Let's also look at the reattachment, we know this should be 6.26. Let's see if this is true. Let's run this again from the start. Let's run it one by one. After 2000, it remained somewhere here. So to make sure that it remains around this particular point, let's run for some more time. We will start from 2000 and run it till 4000. Now let's look at the results again. We'll directly look at the reattachment length, how it is evolving. Let's look at the LIC of this, and from the start, we'll move one step at a time. Clearly it remains around this. Still it is not clear whether it is 6.26. We got to know that even though it does not show a steady simulation, on an average sense, this reattachment is happening somewhere here. We can stop here now and we'll end this course with this. There are various models which are based upon the Reynolds average Navier-Stokes equations. Then within the Reynolds average equation, we have two kinds of model, which one is eddy-viscosity model, which is based on Boussinesq approximation. In these models, we try to estimate the eddy viscosity with the help of the kinetic energy and the turbulent dissipation rate. There are different models. So out of those, the best one is the k omega SST model, which is a blend between the k omega model and the k epsilon model. The k epsilon model works best in the free shear region, and the k omega works best near the wall. The fastest model is the one equation model, which is present in OpenFOAM. There is a zero equation model as well, but that you have to implement on your own. All these models, which are based on the Boussinesq approximation, they assume isotropic turbulence. If you have anisotropic turbulence, which is there in nature and which you cannot ignore, a more correct version of Reynolds average model for turbulence modeling is using our stress model, which takes care of the anisotropy of the turbulence. The best model is the Reynolds stress model, but again it is expensive. You are going to solve for each component of the Reynolds stress. There are more equations compared to other models. Now, whenever you are given a task to run a simulation using the Reynolds average equations, then you will know that which model you should prefer based upon whether the flow is in the free shear, whether there is swirls or not, whether there is reattachment of the flow or there is a separation bubble which you have to take care of. Then depend upon that you can take a call. In industries, in real life, whenever you are simulating something, always try to solve it using k-epsilon model and see what you are unable to capture depending upon the simulation results and the theoretical expectations. Use a more complicated model. So I hope you have learned a lot in this course. See you again in the next course. Thank you.